Okay, can you guys hear me now?
Yes, sir.
अरे कुणाल लवकर सांगायचं, मी 4 मिनिटं मी निवांत बडबड करत होतो आणि यू गायज डिड नॉट रिस्पॉन्ड. मला लवकर सांगायचं म्हणजे कसं होईल, चुकून काय आता माझ्याकडनं म्यूट बटन ऑन राहिलं होतं. इट वॉज माय फॉल्ट, बट जस्ट लेट मी नो द मोमेंट you are not able. No, don't say sorry. It is a mistake from my side. But if you are not able to hear or any kind of issues are there, immediately let me know in the chat, so that we can take a corrective action. Okay, so no problem. So I will repeat. So basically, what we tried to do in this lecture is, uh, okay, I just I had a revision of whatever we completed. So I'll quickly go through the revision part again. Okay, so in the first lecture we have seen the requirement of the spring and different types of the spring, and we have seen the applications where the springs are applied, and materials of the spring and the process for the manufacturing of the spring. And importantly, we have seen, when then we started the nomenclature terminology used in a spring. We have seen that, but there we have seen two important characteristics of the spring. One is spring index, other is stiffness. Spring index is the ratio of the diameter of the coil to the diameter of the wire, right? So we have seen that we will generally use from 6 to 9, right? Less than 3 is not preferred, because if it is less than 3, then the curvature will be high and stresses will be more. And if it is very high, then spring index, then the buckling will be there. So we will use generally from 6 to 9, right? 4 to minimum 4 and maximum 4 is acceptable, but generally we use from 6 to 9. The spring index is ratio of coil diameter upon wire diameter. Okay. Then we have seen different lengths of the spring: free length, compressed length, solid length. We have seen a formula for those. And there we have seen important characteristic of spring is called a spring index K, right? So spring index is basically, if you put a load on a spring, it will be deflecting, and that deflection is proportional to the load. And we have seen that spring index is P upon delta. So it is the unit is Newton per mm. Okay. Then we have seen different types of ends of the spring. It may be plain ends. Then we will take active coils as equal to number of turns. Then if it is grounded, then we will subtract half from it. If it is square ends, maybe normal or ground end, then we will take NT minus 2. We will subtract 2 from the number of turns to get the active coils. We have seen the ends for the extension spring as well. And then we have seen different stresses in the spring. We have seen that mainly there will be two stresses, both of them will be shear, so we will directly add them. One is shear stress because of the direct shear stress and direct shear, and the second is shear stress because of the twisting or the torsion. So we have seen that the torsional shear stress because of twisting is 8 pd upon pi d cube, and because of that direct shear stress it is 4p upon pi d square. So we combine those to get ultimate formula. K tau is equal to shear stress in the spring is equal to K into 8 pd upon pi d cube, where K is wall factor 4c minus 1 upon 4c minus 4 plus 0.615 upon c. Okay, so this is wall factor. We have seen that. And then also we have seen the this load will try to make twist at well, it will twist the spring. So the angle of twist is also coming to picture, and that angle of twist is given by this formula, right? Theta is equal to 16 pd square n upon gd raised to 4. So with that we'll get a deflection 8 pd cube upon 8 pd cube n upon gd raised to 4. So we will need this. So remember this formula: deflection of the spring is 8 pd cube n upon gd raised to 4. It is not very high-fi. Just remember. Then if we have to find the stiffness of the spring, then stiffness is K is equal to P upon delta. So if we will cancel, and we'll get gd raised to 4 upon 8 d cube n. Okay, so we have seen all these, and now today we will go through the design of the spring. Okay, and we'll take a numerical. So uh, basically design is nothing but all these whatever formulas we have seen. The stiffness of the spring is gd raised to 4 upon 8 d cube n. Deflection is 8 pd cube n upon gd raised to 4. Then your the shear stress in the spring is K is equal to 8 pd upon pi d cube, where K is wall factor. So we'll use this formula step by step to get number of coils, length of the spring, the diameter of the coil. To calculate all those, we will use these formulas. So we will see the approach or how we will do the design, and then we'll take a numerical on that. Right? Okay. So as per the summary, whatever we have seen now, there are main three things we are needed. In a spring, that it should have sufficient strength to to take the external load. So whatever load we are going to take, first of all it should be able to take it. It should not fail, and it should have a strength to take that load. Then it should have a required load deflection characteristic. So as per the load, it should have a proper deflection as per the requirement, and it should not buckle. Buckle means it should not fail along sides. Sometimes if that is the case, then we will use guide. So we'll have a rod at the center or at the on the sides, so that it will not buckle. Okay. Sometimes what happens, if the length of the spring is large, then this buckling of the spring might happen. So that time, by using the guides, we will give, we will avoid buckling, and we'll use it in the real life scenario. Okay. So shear stress in the spring is given by 8 PD upon pi d cube. Just now we have seen here C is spring index, d by d. So tau we will get 8 PC upon pi d square. Okay. Now, factor of safety, in case of springs, less factor of safety is used, generally 1.5. Why? Because generally wherever we are using spring, the load is, all those calculations are done more accurately. So if the factor of safety 1.5 is taken, then shear stress is equal to SSY upon 1.5. Okay. So if now we will say shear stress equal to SYT. So generally we will be given SUT or SYT, right? If the SUT is given, then shear yield stress is 0.5 of SUT. So ultimate stress, whatever we have given, will take 0.75 of that as your yield stress. Okay. So now I am explaining you how to take the the limiting stresses. So generally we will be given SUT. So if SUT is given, then we can calculate SYT as 0.75 SUT, and the SSY is as 0.5775 of SYT, right? So now SSY is will be 0.5775 into 0.75 of SUT, right? So I know in the bottom, the next, what you can say, formula we have taken that. So shear stress is equal to SSY, allowable shear stress, upon 1.5 because of the factor of safety, right? So SSY is 0.5775 SYT, and SYT is 0.75 SUT. So shear stress, we will be the shear stress for our design, we can take as 0.3 of SUT. So whatever SUT is given, so why we are taking 0.3? So by using this formula, right? So whatever is SYT or ultimate stress we have given, we will take 30% of that as our allowable shear stress for the spring. So generally, some standards say 0.5. So we can take anywhere between 0.3 to 0.5 of SUT as our working shear stress. Okay. Okay. If somebody has asked me, sir, voice is low. No, why that is the case? Voice is low. Guys, you can hear me or no? My voice is low. Nikita is saying my voice is low. Is that is the case with everyone? Can you guys hear me properly? Reply. Someone reply. Anybody is people who can hear me properly, just kindly reply whether you can hear me properly or not, so that I will continue. Okay. Voice is audible. So Kunal is saying voice is audible. So I will continue. There might be a problem with. Okay, so what I was saying is that allowable shear stress. Now we are going in a design approach, right? How to do the design, and for design we will initially, or the first thing we need is allowable stresses for the materials, right? So whatever SUT we will be getting for the material of the spring, will take zero point 0.3 to zero point 0.5 of that. That means 30% to 50% of that SUT ultimate stress as our working or allowable shear stress, right? Now, once we know that, then we can proceed with our design. So these are the steps which will take. There are few steps, like I think 15 steps are there, for the calculation or the design of the spring. All those 15 steps are whatever we have discussed just now. Okay, so there is nothing new in that. So for a given application, we have to find out the working load on the spring and how much deflection is allowed. So we need two things, that the spring, what kind of load will be there on the spring, maximum load on the spring, and what is the allowable deflection of the spring. So any kind of application, we know that maximum this much will be allowed and load will need to take, it will be this much. So if that is the case, then we will immediately get to know load and deflection, and if we know that, that means we will get to know stiffness of the spring, right? So first step is finding out the load on the spring, finding out the allowable deflection of the spring, and finding out the stiffness of the spring. Okay. Then as per our discussion, whatever next step will be, we have to find out material of the spring. And once we finalize the material on the requirement or the specifications, we have the for this application of the spring, we'll find out the material, and for that material we'll get allowable shear stress as 30% to 50%, 0.3 or 0.5 of SUT, right? Depending on whatever standard you are using. So next step is getting allowable shear stress. This should be actually tau. Let me correct it. It is not T, T is torque. This should be tau. Allowable shear stress is 0.3 to 0.5 of SUT. Now, once we know that, then next thing is to find out or to come up with a spring index. We know that spring index is best is between 8 to 10. So generally, we'll take 8 as the spring index, 9 or 10, depending on your application. It should not be less than 3. For for walls and clutches, spring index is taken as 5, right? It should not be less than 3 and more than 50. Okay, once we know that, then we can immediately find out the wall factor 4c minus 1, where we know c. We can find out 4c minus 1 upon 4c minus 4 plus 0.615 upon c, right? So we know wall factor. So first we know load, deflection, stiffness. We know allowable shear stress. Next step is spring index c, then wall factor. And once we know that, then we can find out the diameter of the spring, because we know what is the shear stress in the spring. Tau is equal to K into 8 PC upon pi d square. Here we know allowable shear stress, we know K, wall factor, we know load, we know spring index, so we can find out diameter of the spring. Right? So using this formula of shear stress in the spring with the wall factor, we can calculate diameter of the spring. Once we know the diameter of the spring D, then we can find out the coil diameter by using capital D by C. D is equal to C into D, right? Because spring index is equal to capital D upon small d. So capital D is equal to C into small d, right? So we know coil diameter. Now we can find out the deflection of the spring, right? We know allowable deflection of the spring, and we have formula for deflection of the spring as delta is equal to 8 PD and PDQ upon GD raised to 4. Here we know deflection, we know load, we know all both D, capital D and small d, and so we know G, right? Modulus of rigidity of the steel, whatever material you have selected. For steel wire, we take it as 81,370. If it is, if the material is, then we can get it from the material, right? So with this, we can find out number of active coils, right? So once we know this, all the diameters, the small d, capital D, spring index, number of coils, then we can, these are N is active coils, right? And we know depending on the ends of the spring, depending on the application, we can add or subtract, half or two to them, and to get the total number of coils, right? So then we have to find out, for that we need to find out ends of the spring. What kind of ends? It will be grounded, it will be, whatever is like regular plane ends or square ends. So depending on the type of ends, we will first finalize the type of end, and once that end is finalized, then we have to add that number, whatever number as per the formula, to get the total number of coils. Because from this formula in step 7, we will or the formula for deflection, we will get the active coils, right? So we have to add that number to get the total coils. So we will get total number of coils, right? Now once we know total number of coils, right? So solid length is now basically NT into D. We know diameter, right, of the wire. Each coil's diameter means diameter of the wire. Total number of turns we know, NT. So solid length, that means when it is completely what you can say compressed, then that length is solid length. Solid length is equal to NT into D, right? Then now we'll find out the actual deflection of the spring, because now this deflection is the allowable deflection, and this deflection is now here because total number of turns N is different, right? So 8 PD cube. Now we know load, we know D and D, but with the N is different now, right? So for that we will find out the actual deflection of the spring delta. Now between each coil, we know that we have seen that each coil must have some kind of gap in between them, right? So because we want, to have minimum some kind of gap, we do not want them to touch each other. So that gap is 0.5 to 2, anywhere between that. So we will take that gap, and that total gap in spring will be NT minus 1, right? So this one we are reducing because of the top and bottom coil. So NT minus 1 into gap between two adjacent coils, right? So if we have two coil gap of 1, then that multiplied by NT minus 1 will be a total gap between the different kinds of what you can say coils, right? So total gap will be NT minus 1 into gap between the adjacent coils, right? In some cases, total axial gap is taken 50%. So whatever deflection we are having D in the previous step delta multiplied by 50% will be taken. So we have to find out total gap using this formula, NT minus 1 into gap between two coils, or we can take some percentage of the total deflection. So now free length means length when there is no any load is solid length, total gap plus delta. Total gap we calculated in the previous step. Delta we know that it is with the now with the modified number of coils, and solid length is used from the formula NT into D. Right. So this way we can calculate all the lengths, and we can calculate the free length of the spring as well. Now, once we know the free length, right, which means when the spring is not having any load, we know the total length of the load. That length upon NT minus 1 will be your pitch. Pitch is what? Distance between two consecutive coils when there is no load, right? So for that, if we have to subtract 1, because whatever number of coils will be there, 1 will be less to find out the pitch. So free length upon NT minus 1 will be your pitch, and rate of the spring, stiffness of the spring. Now this stiffness we have calculated, but because the values have changed in between, so stiffness of the spring is G into D raised to 4 D cube N, because N is changed because of the type of ends. So stiffness we will calculate the whatever stiffness we have got, and then depending on whatever outputs you have got, we will put all the specifications, and we will complete the design of the spring. Okay, so this is how we will do the design. So basically, and at the end, one more thing, at the end, guide is not necessary or guide is necessary. How we will decide that? As I told you, guide is why guide is required. If the spring is the length is very large, that time it may fail because of the buckling. Sometimes it is required to have a large spring, a large length spring. So that time it will buckle. If we put it vertically, it will buckle simply. So for that, why we'll do what we'll do? We'll have some kind of cylindrical arrangement, or we'll have some kind of rod at the center. So whatever arrangement, depending on the application. So that way, that will be behave as guide, and your spring will not buckle, right? And how we will decide that? We know free length, and we know mean coil diameter, right? D. So if the ratio of the length and diameter is less than 2.6, less than equal to, so free length whatever you have got, and mean coil diameter D, if that ratio is less, then guide is not required. But if the free length is large compared to your mean coil diameter capital D, then guide is required. So depending on that, we will decide whether guide is required or not. Okay. So I will quickly go through the design. First, find out the load on the spring, find out the deflection corresponding to spring for that load, and allowable, all allowable load and allowable deflection, and we find out the stiffness of the spring, expected stiffness, right? Then we'll find out the allowable stresses, 0.3 or 0.5 SUT. We'll find out, calculate the spring index. We'll take 8, generally 8 to 10. Wall factor using 4C minus 1, 4C upon 4C minus 4 plus 0.615 upon C. Determine the small d, then determine capital D, determine the total active number of coils using deflection equation. Then calculate, find out the finalize the ends, and calculate total number of coils NT. And once NT is finalized, then calculate actual deflection delta. So calculate solid length, and then actual deflection delta depending on the number of coils. Then find out the total gap, NT minus 1 into gap between two coils, or you can take some percentage of maximum deflection. Find out free length, and once we know the free length, you can find out pitch and actual stiffness of the spring. And at the end, whether the guide is required or not required will decide depending on the ratio of free length and mean coil diameter. Okay, so this is how the design is done. So if you guys have followed it, and you guys are okay with, I will go ahead with the numerical on that. Okay. Okay. Okay, so let's take a numerical. Now, basically, we'll try to design a spring with whatever approach we have seen. The Problem statement is that it is required to have a design of a helical compression spring to subject it to maximum force. So load on the spring is given as 1250 Newton. Okay. So spring is having a load of 1250 Newton and deflection for that maximum force is 30 mm. So we know deflection delta. This is allowable deflection and load is given. So we immediately know that stiffness is 1250 and upon 30. So it will be 125 upon 3. So 141 point, I think 66. Stiffness will come to 41.66, something like that. Okay, so spring index is taken as 6. So they have given the spring index C as 6. So ratio of capital D upon small d is 6. So we know that spring is made of a cold drawn steel wire, and the shear ultimate tensile strength and modulus of rigidity, both of them are given. So SUT is given as 1090 Newton per mm square, right? So we know SUT, and modulus of rigidity is 81,370 Newton per mm square. So G is given and SUT is given, right? So SUT, we know that we can take some ratio of that as our allowable shear stress, and G is given. We will need it for the deflection equation. Okay. Permissible shear stress for the spring wire should be taken as 50% of the SUT. So they have also given the tau is 0.5 of SUT. So tau will be half of 1090, so it will be 545. So 545 Newton per mm square will be your allowable shear stress. So we have to design the spring and find out wire diameter. So we have to calculate wire diameter is what? D small d, mean coil diameter capital D, number of active coils like N, we have to calculate, number of total coils NT, free length of the spring. So this will be solid length plus deflection, right, plus allowable gap, right, and pitch of the coil. So 1 for the free length upon NT minus 1 will be your pitch of the coil. Draw sketch of the spring showing dimensions. Okay, so this is the problem statement. So you guys are following the problem statement. So it is pretty straightforward. Load is given, deflection is given, spring index is given, SUT, tau is equal to 0.5 SUT, and G is given. So what is given? P is 1250 Newton, deflection is 30, C is 6, SUT is given 1090 Newton per mm square, G is 81,370 Newton per mm square, and tau is equal to 0.5 of SUT. So this is what is given. So we'll take the approach whatever we are seeing, and we will try to design the spring. Okay. So you guys are with me? Guys, you are following me. You guys can hear me, and you guys are following me. Participants, who is there? Who is awake? So Konal and Rutura saying yes. Okay. So I will try to solve the problem with the approach whatever we have seen. Voice is breaking. Okay. So today I think we generally don't get any complaint about the voice, but today we are getting. But I don't know, because I checked everything and everything looks fine to me. So anyway, but even though it is breaking, if you can hear me intermittently, still you will be able to follow, because we are trying to solve a numerical term. Okay, so first we'll find out wire diameter, that is small d. So we know tau is equal to 0.5 of SUT, so it is 545 Newton per mm square, 0.5 of 1090, and wall factor K is equal to 4C minus 1 upon 4C minus 4 plus 0.615 upon C, right? So that C is given as 6. So your wall factor comes to, you inputting this formula, 1.2525, right? So now we know. Okay, so now we know wall factor of the your spring, right? So now what we will do, we'll try to find out, we use the shear stress equation and try to find out small d, like that is wire diameter. So tau is equal to K into 8 pc upon pi d square. So we know tau 545 allowable shear stress. We calculated K 1.2525. We know load, we know C, so we can find out small d. So small d will come with this equation, that is diameter of the wire will come to 6.63 in, or we will take, because we cannot manufacture a wire with 6.63, so we will take 7 mm as the wire diameter. Okay, so first step we have calculated with the given information, we calculated allowable shear stress, wall factor, and using that we calculated the diameter of the wire of the spring. Now we have to calculate cap D, capital D. Now how we can calculate? We know C. C is equal to what? 6. So C is equal to D upon D. So 7 into 6, 42 will be your mean coil diameter, right? So it is C into D. So 6 into 7, 42 mm will be your mean coil diameter. Now we have to find out active coils, and then we will finalize N to get the total number of coils. How we can calculate active coils? Delta is equal using deflection equation. We know deflection, we know load, we know capital D, small d, and we know G. So we can calculate total number of active coils. So delta is equal to 8 PD cube N upon GD raised to 4. So we'll put value of delta as 30, P as 1250, D as 42. We just calculated that. Small d as 7 and G as 81,370. So with that, we will get number of active coils. I mean, these are the coils which are actually working, helping in spring in that action. Is N is equal to 7.991. So we'll take rounded to 8 coils. So there will be total number of coils of the spring which we are in the action will be 8. 8 number of coils will be working or taking the load. Now we have to find out total number of coils. How we can find total coils is we'll try to finalize the end. So we'll take square and grounded. Generally that is preferable. Square, if the square end is there, then total number of coils will be active coils plus 2. We have seen that, right? So NT, total number of coils, is equal to N plus 2. That is 8 plus 2 is 10 coils. So our spring will have spring index C as of 6, and the total number of coils will be 10 coils. So there will be 10 coils. Now we know number of coils, we know deflections, all that. So we will try to find out the length of the spring now, different lengths of the spring. Okay. So actual deflection. So this deflection we have used, right? It is the deflection which was required or the allowable. So but number of coils is changed now from 8 to 10 because we have approximated 7.91 to 8, and also we added 2 to get the total number of coils. So now we'll find out the actual deflection of the coils. Because of this approximation, we have this deflection is standard, but our approximation we have to find out the actual deflection of the spring. 8 PD cube N upon G raised to 4. So 8 PD is P is 1250, D is 42, number of coils is 8. We are not taking 10 because the last and these 2 coils will not be in action. They are not part of the deflection process. They will be touching the object, so those will not deflect. So delta will be this now because of 8, the delta will change. See now only difference between this and this is the value of N. Here N was 7.991, here N is 8. So actual deflection we will get, let me just change the color. Actual deflection of the spring is whatever is that. Okay, 30.34. So delta deflection of the spring. So initial deflection was, what was the deflection? 30, but actual deflection will be 30.34 because of the number of coils. Okay. Now once we are there, we know the solid length of the spring. Total number of coils is 10. We have got, right? I multiplied by deflection diameter of the wire 7. So if the spring is completely compressed, the solid length of the spring will become 10 into 7, 70 mm. So when the spring is completely compressed, everything touching each other, then the length of the spring is 70 mm. Now we have to finalize some gap between each adjacent coil and find out the free length, right? How we can find out the free length? Free length is equal to solid length plus gap plus delta. Okay. So if the gap is 1 mm between each consecutive, and there are 10 coils, right? So if there are 10 coils, 10 rounds are there, subtract 1 from it. So we'll have 9 gaps, and each gap is 1 mm, that is assumed. So total gap will be 9 mm. Okay, I will repeat again. If now we have got the total number of coils as 10. So gaps between each coil will be, there will be 9 gaps, and each gap is 1 mm is assumed. So total gap is 9 mm. So we know solid length 70 mm, total gap is 9 mm, and deflection whatever we have got is 30.34. So we can get the total free length of the spring as solid length 70, gap 9 mm, and deflection allowed on the spring 30.34. So that is 109.34. So total will take the free length of the spring when there is no load or it is free, that is 110 mm. So we'll have a spring with 10 coils, 110 as free length, right? So now we can find out the pitch, right? Now we know total length of the spring is 110 mm, and what is pitch? It is this distance between two adjacent coils, right? So how we can calculate that? Pitch is basically free length 109.31 upon nt minus 1, or this we can take as 110 also, free length. So 110 upon 10 minus 1. So because pitch, for pitch the total gaps are 9, right? Not 10. So nt minus 1. So that will comes to 12.15. So pitch of the coil is 10, pitch of the coil is 12.59 mm. Pitch means distance between adjacent coils. So we have got all the information required for the spring, right? Which is basically we have calculated, what I can say, we have given some information. We calculated small d, capital D, number of coils in action, total number of coils. With that we calculated the actual deflection. Then we calculated solid length of the spring, nt into the 70 mm. Free length is equal to solid length plus total gap. We consider gap between each adjacent coil as 1 mm plus delta deflection allowed, and then we calculated the pitch of the coil as free length, whatever length we calculated upon nt minus 1, so it comes to 12.15. So this is how the spring will look like, when we design it. So this is how it looks like. See, now 110 is your free length, so total length of the spring is 110. Pitch is distance between two adjacent coils is 12. So I'm showing you diagram to have a much better comfort level or understanding of the spring. So 110 is total length, distance between two adjacent coils 12.5. Diameter we have got 7 mm as the wire diameter and 42 as the mean coil diameter, capital D. So 42 is 7 times 6. So it is 42. So mean coil diameter is 42. Wire diameter is 7. Distance between two coils, adjacent coil is 12.15, and total length is free length. This is free length is 110 mm. Okay. So this is how the spring will look like, right? Now 42. Now this is the diameter of the spring, right? So 42 minus 7 will be the inner diameter of the coil, and plus 7 for 914 as outer diameter, which is shown at the top. So 49 is what? 42 plus 7. Outer diameter is what? Mean diameter plus half on this side, half on this side. So plus diameter. Okay. So total diameter of the coil is as shown in the figure. Okay. So this is how the spring will, look like when we complete the design. Okay. So you guys are with me. You guys followed whatever I explained. So this is how we will design. So this, this numerical had a complete design of the spring. So next time we will try to go ahead with the series and parallel. What are the spring, series connection? We can put the springs in parallel or in series, and how to stiffness will vary in those cases. I will take a numerical also. Okay. Okay. So today we have gone again. We had a revision on the stresses of the spring. We again went through different formulas of the spring, of the deflection, number of coils, shear stress, wall factor, right? And then we have seen the approach of the design of the spring, how to calculate, assume what, and how to find out stiffness, load, deflection, allowable shear stress, wall factor. Then find out the small d, capital D, number of coils, find out the total number of coils, find out solid length, find out the actual deflection, find out total gap, to find out total free length. After free length, we can calculate the pitch, and then we can calculate final stiffness. Okay. So, and then we took a numerical and we have solved the numerical. Okay. So you guys are, if you have followed, just give me thumbs up. Let me know you guys have followed, and we can close today's session. Okay. Thank you guys. If you guys don't have any kind of query or questions, then you guys can quit. Okay. Save the attendance, and thank you for attending the lecture. Guys, lecture is done. So if you guys are hearing, it is done. So you guys can quit. If you guys are serious, that means you guys were not listening at all. Okay. Anyway, thank you guys.